So let's do small recap. So whatever we have completed so far. So we have seen damped single degree of freedom system of spring stiffness K and damping coefficient C. So what we do, we need to draw free body diagram. So it's a perturbation. So these are the forces we experience. So then the governing equation with the boundary condition. So from this we will get characteristic equation like minus c plus or minus root of b square minus 4ac divided by 2m. So these are the roots. So based on these roots we will get three different type. So the case 1 will be c square equal to 4km. So this is critically damped system. So example of critically damped system is the speedometer dial in our automobile. So whenever there is a change in speed, it has to immediately respond to it. So therefore it has to be critically damped. So thereby the response will be faster. Case 2 will be c square greater than 4km. So it is over damped system. So example is the door stopper. So in typical door stopping mechanism is over damped. So case 3 is under damped system where c square less than 4km. So typically some inertial sensors so will be come into this region, and even some buildings and lot of other things will come into this. So where where we need the system to be in under damped systems. So now we move into forced vibration. So let's start forced vibration. So here it will be similar. So we have spring, one damper with mass m. So we are giving perturbation of x. So in the free body diagram we will get, because of this mass, we get mx double dot kx cx dot, and we have, there is a force is acting here, f of t. So capital ft. So this force I am representing as like this. So now equations of motion becomes so this is equation of motion. So we need to find the solution for this. So since this is non-homogeneous equation, so the solution will be of this. So we need to find complementary function, and we need to find particular integral. So complementary function is solution of homogeneous equation. So we will find xcf first. So to find this xcf, so we need to consider homogeneous equation kx equal to 0. So this is what we have solved in previously. So by this time you should remember this result, x of t e power minus neta omega t a cos omega dt plus b sine omega dt. So this is you should remember. And next one is x of pi. We need to find this. To find, we need to consider this but non-homogeneous equation. So far we don't know what this f is. So here we say this f is some p is the force e power I lambda t. Lambda is the forcing frequency. So in mathematics, so the solution will be similar to the forcing. So therefore the solution x of t will also have the same frequency of the forcing. So I lambda t. So here this I lambda t means cos lambda t plus I sin lambda t. So here you can ask why there is an imaginary part in the forcing function. So this is for our convenient. So we will get the result x of t that will also contains real part and imaginary part. If you consider real part, that is the solution of this cosine forcing. If you take imaginary part of the solution, then it is the solution of sine forcing. So depending upon our convenient in future, we will choose which one we are interested in. So let's continue this. So we will substitute this assumed solution into the equation. So then we will get so this one gets simplified like this: k minus m lambda square plus I lambda c. So here we do some simplification. So we want to write this in terms of neta, omega, neta and omega. So to do this, we need to introduce these parameters. So which one is neta? C is equal to what is C is equal to? We don't know. So we will start from the neta. So neta equal to C by C critical. So C become to neta into C critical. So C critical equal to 2 root km. So 2 root km we can write 2 neta m omega. So we use this formula, and instead of k by m we substitute omega square. So then we can convert into above equation into x equal to, so p divided by, so we will take k outside, so k outside, so therefore 1 minus m divided by k lambda square plus I lambda c by k. So therefore we can write p by k into, so 1 minus m by k becomes omega square. So this is one, and plus lambda we know c by k. So how we can write this? Lambda c by k. C becomes 2 neta m omega we can write. So 2 neta m omega lambda divided by k. So k by m becomes omega square. So we can, this part can be written as 2 neta omega 2 neta k by m becomes omega square. In the bottom omega is there, so this omega get cancelled, so this become omega 2 neta lambda by omega. So we introduce another term, so lambda by omega is r, so is the ratio of two frequency. So when we include this one, so the equation become, and another part, so x st equal to p divided by k. So p is the forcing, k is the stiffness of the spring, so p by k becomes static loading. Static deflection. So this will get simplified like this: 1 minus lambda by omega whole square plus I 2 neta r, 1 minus r square 2 neta r. So now I want to get rid of this imaginary value at the numerator. So for that I am multiplying with 1 minus r square plus I 2 neta r into 1 minus r square minus I 2 neta r divided by 1 minus r square minus I 2 neta r. This becomes x st 1 minus r square minus I 2 neta r divided by 1 minus r square whole square plus 2 neta r whole square. Then this becomes minus, so because of this imaginary value, so we can write this thing as this is our simplified form of x. So then the solution x of t will be capital X into e power I lambda t. So therefore this becomes x st 1 minus r square minus I 2 neta r 1 minus r square whole square minus, so this become plus, plus 2 neta r whole square, e power I lambda t. So here we can simplify further using this. So I can simplify these things into, so assigning the value r cos theta, so r sin theta, so this is also r cos theta. So now this term becomes x st, so r of cos theta minus I sin theta e power I lambda t. So here this becomes r of cos square theta plus I, there is no I, sin square theta, so this becomes 1. So now here it is r square, so since r is taking out, this one cancelled, and x st e power minus I theta e power I lambda t divided by r. So where theta is, so tan theta is cos theta minus sin theta, so sine by cos, sine theta by cos theta. So what is sine theta? 2 neta r cos theta 1 minus r square. So theta is tan inverse of this, where r equal to, r is cos square theta, sorry, so r is the radius, so radius equal to r into cos theta whole square plus r into sin theta whole square square root. So this becomes so what is r cos theta? So this provides r. So then what is r equal to? So we will substitute it, 1 minus r square whole square plus 2 neta r whole square square root. So now we need to substitute this, xst divided by 1 minus r square whole square plus 2 neta r whole square e power I lambda t minus theta. This is x of t of pi. So now we successfully found the equation of this particular integral. So the another parameter I need to introduce is the d. So this is dynamic amplification factor. Which is xst divided by this root 1 minus r square whole square plus 2 neta r whole square. So this is dynamic modification factor because this value depends upon the, so not xst, this is 1. So this depends upon purely frequency r. Now we write full total solution. So total solution x of t equal to particular integral plus complementary function, so which is e power omega t a cos omega dt plus b sin omega dt plus exst divided by 1 minus r square whole square plus 2 neta r whole square square root e power minus, not minus, I of lambda t minus theta. So theta you know. So now we need to include the boundary condition. So we need to find solution for this. So before I will find x dot of t becomes, so I am using UV rule. So xst divided by this dynamic modification factor will not change, so therefore only lambda t will come. So let's find x of 0 equal to a, b becomes 0, plus xst divided by d into when lambda t is 0, so e power minus I theta will be there, right? Yeah, so now x equal to x naught, therefore a equal to x naught minus xst divided by d into e power minus I theta. So now x dot of 0 equal to b omega d will be there, eta omega of a cos omega d is there, so that will give a plus xst divided by d lambda t e power I theta minus, therefore here we substitute a, which is x naught dot bwd minus eta omega so here now we find x naught, we found x naught, so let's write it down, try to expand it. So this is x naught, this is oh, we need to find b here, so b equal to, that is our idea, so b becomes x naught eta omega minus eta omega xst divided by d e power minus I theta plus xst divided by d lambda t e power minus I theta divided by omega d. So then we substitute this a and b, so a is here, b is here, a and b into the equation, so if we substitute this a and b here, then what we will get, let assume, so believe me, so if we take only real part of everything, so we will get, so if the force p is equal to p f is equal to cos lambda t, that is what we considered, see e power I lambda t, so if p is equal to only cos lambda t, the derivation becomes very simple, you can do it, if you do it you will get the equations, x of t will be similar to this one, So this is almost same, it's very same, okay, very same as the equation we got here. Where is x of t? Yeah, we got here. So now what we do, so if we substitute our boundary condition, we will get yeah, this is the solution of forced vibration.